Okay, so let me remind you where we left off, although we're going to kind of start with a new topic almost for the last lecture. So where we left off was we were interested in, we described the quantum cohomologies for affine Grassmannian slices and for quiver varieties. Then we wanted to describe, then I said, oh, it's very interesting to try to compactify the space of the parameter space for these quantum cohomology algebras. So a priori, it's parameterized by this open subset of the torus. And we were interested in compactifying this parameter space. And I described last lecture how this parameter space is compactified into the Deligne-Mumford space of genus 0 curves in the case of affine Grassmannian slices. And then I said over this compactified parameter space, or maybe over a real locus inside of it, we can form a topological cover given by eigenvectors for those algebras acting on our cohomology. And our goal was then to describe the monodromy of this cover. So that's what we're going to do. But before we do that, we're going to have to do like a weird detour. That's what we're going to start with. OK, any questions about that? OK, let's start with the weird detour. So you could imagine you just came in, you hadn't heard the rest of the lectures. OK, so let's G be a semi-simple Lie algebra. And we're going to be interested in, well, maybe not that surprisingly, we're going to be interested in tensor products. Sorry, I got to get my thing. We're going to be interested in tensor products of irreducible representations. So let's say an n-fold tensor product of irreducible representations. And let's say our goal is to find a basis of this space, of this n-fold tensor product. Many ways to find bases for representations, but this is one way. One way to find a basis for the representation is to find a large commutative subalgebra inside of the universal enveloping algebra. Well, in fact, inside of the universal enveloping algebra, tensor with itself n times, since that's what's going to act on this tensor product of n copies. So we'll find a commutative subalgebra, and then we're going to hope that under this action of this commutative subalgebra, we can decompose this tensor product into distinct one-dimensional submodules. So large commutative subalgebra, you should think of like the generators of the subalgebra will be some commuting linear operators. So I have a bunch of commuting linear operators acting on this vector space, and I want to simultaneously diagonalize them. And when I simultaneously diagonalize them, I hope that all those simultaneous eigenspaces are one-dimensional, and so I'll get a basis. So there's like our obvious commutative subalgebra inside a universal enveloping algebra, which is coming from the Cartan subalgebra, or the universal enveloping algebra, the Cartan subalgebra. But typically, that won't diagonalize our vector space into a direct sum of one-dimensional submodules because, of course, there's weight multiplicities. Okay, so if we had maybe if we had one representation that happened to have no weight multiplicity, then it would be enough just to take the Cartan subalgebra. But we have big tensor product of representations. Maybe each one is not too complicated, but we have this big tensor product. So we have some weight multiplicities. So it's not enough just to take this Cartan subalgebra. We need something more complicated. But we'd like A to contain this Cartan subalgebra, or diagonally embedded Cartan subalgebra, so that the basis we obtain is a weight basis. OK, so how can we proceed? Well, we proceed as follows. We're going to start by introducing certain elements called inhomogeneous Gaudin Hamiltonians. And those elements will be sort of like the building blocks of our commutative subalgebra. Not quite the generators, but they'll be in there. So they're going to depend on a parameter. We're going to start, or two parameters rather. So here's our two parameters. One parameter will be an element in the Cartan subalgebra, in the regular part of the Cartan subalgebra. So it pairs non-zero with every root. And the other will be n distinct complex numbers, kind of like before. And from the viewpoint, if you're thinking back to what we were doing like last time, this theta has to do with the equivariant cohomology of a point, and this z has to do with this quantum parameter. So here we have a kind of equivariant parameter and a quantum parameter. So we pick those two guys. We form this thing called the inhomogeneous Gaudin Hamiltonian as follows. So remember, we had originally we were talking a lot about this thing, this Gaudin Hamiltonian, which is the sum over linear combinations of inserting this Casimir in the ijth spot. And so I do that, but then I add an inhomogeneous term, an extra term, which is the result of inserting theta, this element in the cartan, in the ith spot. So this is an element in UG tensor N. Okay. Now, sort of fundamental theorem for us of Fagan-Frankel-Rybnikov is that there exists a sort of unique maximal commutative subalgebra inside this tensor product which contains these elements. Oops, I noticed the theta is missing here. Which contains these elements. So I have those n elements. They're now linearly independent. They define an n-dimensional subspace. And I can extend this subspace to a certain maximal commutative subalgebra. So unfortunately, the definition of this maximal commutative subalgebra is sort of complicated, so I won't get into it. But it is kind of a natural construction and a sort of universal kind of construction. So now, if we're going to be interested in the following thing, we're going to fix theta, so this element in hreg, and we're going to imagine the z varying, which is much like what we did like last time. Yeah? Chi is just like a different letter for theta. Thank you. For some reason, it's quite possible that chi will slip in because somehow I usually used chi, and for some strange reason I said switch to theta today. But if you see a chi, it surely should be a theta. Okay, so previously when we just had this homogeneous term, our subalgebra was invariant under both scaling and translation. But now if we do translation, okay, nothing changes because we have a difference here. But if we do scaling, we're actually going to get something different because this term will get scaled, but this term won't get scaled. So the algebra will change. So if we imagine fixing the theta, of course we could compensate by changing theta, but let's fix theta. So for fixed theta and varying z, we get a map from n distinct points on the complex line modulo translation to the space of subalgebras. So you might say it's just like what we had last time, but last time we had like also scaling here. We don't have scaling. And for some reason, it makes an enormous difference. It looks like a small difference, but it makes a very big difference. So now we pose the same problem I posed last time. We get a map from this parameter space to the space of subalgebras. We take the image, we take the closure. What space do we get? And last time we said, oh, we got this supernatural space, the Deligne-Mumford compactification, which is just like a moduli space of these stable genus zero curves. Now, surprisingly, we get a new space, at least I believe. It does not appear in the literature before our work. Okay. So some of the reason why something new happens is because there's like, well, okay, let me explain. So first of all, imagine we weren't modding out by delta. We're taking the vector space Cn mod C. Well, how can you compactify a vector space? There's this, I would say now famous construction called Matroid-Schubert variety, which is only 10 years old, but been very influential in combinatorial algebraic geometry in the past 10 years. A very natural construction for compactifying a vector space. Let's see how it works. So let's start with the vector space Cn mod C. I want to embed Cn mod C inside C to the n choose 2. Okay, so my compactification will depend on how I embed it, but I'm choosing this embedding, which I claim is a sort of natural embedding. So how do I embed it? Well, on Cn mod C, what are my natural linear functionals? I can take the difference of 2 points. I mean, Cn mod C is n points on C modulo translation. The difference of 2 points will be a well-defined thing. So I can take all possible differences. I call those things delta ij's. So I get n choose 2 differences. Those differences must obey some equations, right? Like distance from I to j plus the distance from j to k is the distance from I to k. So in fact, you can see from this that Cn mod C is naturally a subspace of C to the n choose 2, the subspace defined by those linear equations. Okay, basic linear algebra, nothing interesting happening. Now all of a sudden something interesting happens. I allow these elements of C to become elements of P1, and I impose the same equations. So at first glance, it looks like can't be too interesting. I have like the equation like kind of like A plus B equals C. But what's happening now is that I'm allowing the distances between the points to become infinite. So I've compactified C to P1. So for every 2 points, I can allow the possibility that their distances should be infinite. And because of the equations, it forces us into the situation where the points, every inside this new space here, there's a set partition of 1 up to n. And within every part of that set partition, the distances are finite. And the distances between points not in the same part are infinite. So here's an example. Here I have these first 3 points here, these points here, and these points here. And the distances across these things are all infinite. So between any 2 pair of points across, the distances are infinite. And in each group, the distances are finite. So every point in this compactification, this matrix-Hilbert variety, will look like that. So whereas before I had n points on C modulo translation, now I have the possibility that my single copy of the complex line could break into multiple affine lines. And I get points on each affine line. And on each affine line, I consider those points up to translation. So an element of this matrix-Hilbert variety can be thought of as a collection of such complex lines with points on them modular translation. And for some reason, we decided that it's not so pretty to have different complex lines floating around. It would be prettier if you just join them, if you imagine each complex line forming the petals of a flower. And so it makes for a prettier picture. So we picture the points of this space as these flowers. So you have these lines here got kind of wrapped around and became a line like that. OK, so you might think this variety, it can't be too interesting. It's just defined by some linear equations. Well, here, let's take a look at the simplest case, C3 mod C3 bar. So it's defined by 3 points, A, B, C in P1 cubed, satisfying the equation A plus B equals C. So surprisingly, if you take the very simple equation A plus B equals C, it's singular. Doesn't look like a very singular variety. But imagine you expand this equation in the neighborhood of infinity. So you replace A with 1 over x, B with 1 over y, and C with 1 over z, and clear the denominators, and you'll arrive at xy plus yz equals xz, which is a singular variety. So in the neighborhood of the all infinities point, it looks like a cone point. So this variety C3 mod C is singular. In fact, every variety Cn mod C is singular. OK, so this is not the answer yet to our question, but we're on the way to the answer to our question. Any questions about this guy? Okay. So in this space, Cn mod C bar, in this matrix-Hilbert variety, I explained that it's a bunch of different copies of the point in this space is a bunch of copies of A1. On each A1, I have some marked points, and so on. But we could still have equal marked points. I didn't disallow the possibility that delta ij is 0, right? There's no reason why I couldn't have delta ij as 0. And delta ij being 0, well, it means that between the 2 marked points is 0, so the marked points are equal. So in this space here, there's this problem, which is at least sort of a problem from our perspective, it turns out, that there could be still equal marked points. So what we do to get rid of the problem is we do a kind of iterated blow-up of this Cn mod C bar along intersections of the loci where delta ij is 0, which has the effect that in terms of the points, so if you imagine here, we might have had, say, imagine these 4 marked points. They might have all been sitting over here. But now we allow them to bubble off and go on their own P1s. And these extra bubbled parts, these behave just like the usual Deligne-Mumford business. So here we have a bunch of P1s connected according to a tree, nodal singularities, and the stability condition. And maybe most importantly, they're considered up to their full automorphism group. Whereas these other ones here, these other components of the curve over here, are considered only up to the action of the additive group. So up to translation. So in this new space, we picture them, points of this new space, we call it cactus flower curves. There's a flower, and on top of the flower is growing a cactus. That doesn't happen in real life. In real life, the flower can grow on top of the cactus, as you see in the picture. I saw it on Wednesday. But here we have cactus growing on top of the flower. Okay. So this has been a little vague, and in fact, it turns out to be a pretty hard problem to write down an exact moduli problem that Fn bar solves. So it's still an open question to formulate the moduli problem solved by Fn bar. There was another person, Adrian Zariuk, who was not quite studying the same space, but a somewhat similar space. From what viewpoint? I have no idea. But I mean, from algebraic geometry motivation. And according to him, and I believe him, the right structure to put on each of these blue components is a differential, is a section of the a section of the cotangent bundle. Okay. So it remains an open problem to describe exactly the moduli space precisely, but this Fn bar, we have a precise description of it. Like, I can tell you exactly the charts and everything on that space. Any questions?
Maybe about the algebra at the beginning. The x theta, what exactly was this inhomogeneous? In what way is this inhomogeneous?
Why did I call it inhomogeneous? This thing here? Well, because this term is like degree 2, and this term is degree 1. I think that's why it's called inhomogeneous. Yeah. Okay. So in this work, well, with all these authors here, maybe I won't try to read out the list of authors. We defined this space Fn bar, and we proved the following. We constructed a deformation of it, which is like a slightly scripty looking F over here. So it's something which maps to A1. The fiber over 0 is this Fn bar, and the general fiber is this Mn plus 2 bar. So this is just the usual Deligne-Mumford space. So point here, the points in this space here are we just have a usual, guys like this. Some marked points. But two of the marked points are kind of distinguished, like the n plus first and the n plus second, or maybe the 0th and n plus first, let's call it. So here I have a 0 and an n plus first marked point. And somehow, the way you should picture this degeneration is in some sense, these two marked points are getting closer together, and in the limit, you somehow, they both disappeared and became this kind of funny central point here. I don't have a precise statement, but that's a vague intuition about how this degeneration works. But it's possible just to write down this degeneration just in equations. It's not so hard.
So do you have a similar feature for the commutative subalgebras? Like there is a one.
Yeah, we're getting there.
You are going there.
We're heading there. Ta-da. So we proved in a second paper that, so first is we had, okay, this map, so the thing I started today's lecture with, which was this inhomogeneous Gaudin algebra. So remember that depended on n distinct complex numbers, modulo translation. So the first part of the theorem is what I sort of said already verbally, that this map compactifies, like the closure of the image is precisely this new space Fn bar. So we had to invent this new space Fn bar exactly because it was the closure of the image of this map. We were forced into it. And so we get a map from this Fn bar to this space of subalgebras. And even it works in families, like it works, sorry, in this deformation. In this deformation, we get a map from this deformed Fn tilde to the space of subalgebras, which on the 0 fiber is this map. And when A is not 0, this map here becomes the map which I talked about last time, which associates to every point in Fn bar this trigonometric Gaudin subalgebra. So this guy is the guy that's going to go over to the quantum cohomology. Well, this part is sort of still conjectural, although proven on the quadratic level, that this goes over to this quantum cohomology. So in some sense, well, from the viewpoint of the first few lectures, it's really this guy that I'm interested in, but now I've put it in a bigger family, and this central fiber turns out to be kind of, while the space is hard to understand, these algebras turn out to be kind of easy to understand. That's the reason why we construct this family, you could say.
So A theta z axis on the
No. No, actually, it's an interesting question. I don't know any geometric meaning. I don't know a geometric interpretation of this. So this one is related to quantum cohomology. And one special point in this space is related to the ordinary cohomology. But all the rest of these algebras, I don't know any interpretation of them using cohomology or anything geometric. Strangely enough. So all of these, at least for the non-generic, for the generic Zs here, all of these spaces are quantum cohomology algebras, or when they act, they become quantum cohomology algebras. This one, in a very special case, is an ordinary cohomology, and the rest of them, I don't know what they are. Algebraically. I mean, geometrically. I mean, I do know what they are algebraically. I don't know what they are geometrically. So from this geometric viewpoint, this one is sort of much easier to motivate than these guys. But these guys are sort of easier to understand from algebraic viewpoint. Any other questions? Okay. So now there's a special real locus we defined, which I won't get into exact. Well, I'll tell you a little bit more about its definition soon. But there's a natural real locus of this space, and we proved that for any point in this real locus, this algebra, this inhomogeneous Gaudin algebra, or this trigonometric version, when you take this a not equal to 0, so these algebras, they do what we want. They act semi-simply on this weight space of the representation with simple spectrum. And so this is the desired property. We get this desired property for these quantum cohomology algebras. So this, the fact that our algebra acts semi-simply with simple spectrum, that means it decomposes this weight space of the representation into one-dimensional spaces, and it leads to this cover. So the cover, the fiber over some point, is just a set of eigenlines. Maybe we should call it eigenlines. Eigenlines for the action of this algebra. And so this gives us a unramified covering, topological covering of our space, and the fibers of this covering are just given by the set of eigenlines, so the number of those eigenlines is equal to the dimension. So we get an unramified covering where the cover is a finite set of the size equal to the dimension. And now we have a cover, and as I mentioned, like when I discussed this a while ago, when you have a cover, it's natural to ask, what's the monodromy? So if you have a covering, you get an action of the fundamental group of the base on one of the fibers. So we have an action of this fundamental group of the base on this finite set.
Do you expect that this theorem holds in other situations, like for finite ID equivariate? Do you expect something like this, like that you have a family that different for A, different from 0, you have quantum multiplication, and then there is some kind of fiber algebra that is some other algebra?
Yes, basically. Well, you can discuss with Lenny after, but yeah. Basically, yes, but it's maybe not as easy to see what's going on in the equivariety case. So everything is a little bit more complicated in the equivariety case.
But there is something that should play the role of this Carly F bar for the Concini Gaifi.
Yeah, so it'll be, we expect it'll be like the general fibers will be this De Concini Gaifi, and this special fiber we haven't not defined yet, but it should be sort of an analog of this thing for that other root system. So it would involve this Matroid-Schubert variety of the other root system blown up. But there's something a little bit more complicated which might happen because there's already this, there's a work of, it's getting a little off topic, but there's a work of Balabanu, Crowley, and Lee, not published yet, which is about degenerations of this toric variety to this Matroid-Schubert variety. And they don't just get a single Matroid-Schubert variety, they get a union of Matroid-Schubert varieties. So it's possible that what you get in the central fiber might be a blow-up of a union of Matroid-Schubert varieties. So picture may be more complicated in that situation. Do you agree, Lena? Okay. But yes, roughly speaking, the same thing should hold. But it's not worked out yet. Okay, so So as I said, now our question is, what's the covering? What's the monodromy of this cover? So the first question you might ask, what's this fundamental group with a base? So in this same work, well, one of the two papers, we studied the topology of, we studied the fundamental groups here. So again, remember the picture, we have this total space. So the fiber over 0 is this Fn bar, and the general fibers are these Deligne-Mumford spaces. So these are just ordinary, usual, nice, smooth Deligne-Mumford spaces. We'll get back to this guy in 1 second. So our theorem we proved in this paper is the following, that we have a map. So the inclusion of the general fiber gives us a map on pi 1, and the inclusion on the special fiber also gives us a map on pi 1. The inclusion of the special fiber actually is an isomorphism on pi 1. So this is an isomorphism here. This is an isomorphism. This one is not an isomorphism. In fact, it's injective. The fundamental group of this space is something called the virtual cactus group. I'll get to its definition soon. And the fundamental group of this space is something called the affine cactus group. We'll get to that soon too. Okay, so we're able to give a description of the fundamental group of the special fiber and the general fiber, and we prove that the special fiber is fundamental group of the special fiber is isomorphic to the fundamental group of the total space. Okay, so a couple of caveats regarding this theorem. So the first caveat is, you might have noticed I introduced some weird sigma around here. This sigma is to indicate that the real structure we're using on this, so this again is this mn plus 2 bar is my notation for the Deligne-Mumford space of genus 0 curves with n plus 2 marked points. And this sigma sitting around here is just indicating this is not the standard real structure. So what real structure is it? We have a curve, genus 0 curve, defined over R. So one of those unions of P1s, defined over R, and n plus 2 marked points. And most of the marked points are real. They live on the real locus, but not the first and the last one. Those two are actually complex conjugate with respect to this real structure. Okay, so there's like there's a standard real structure where all the points would be real, and then there's these different other real interesting real structures where you consider different pairs of marked points that are complex conjugate. So here we just have 2 pairs of complex conjugate points, and the rest of the points real. And the second caveat or something about the theorem is that you might have noticed I snuck something Sn here. So there's an action of Sn on everything, and it turns out to make the thing work better, we should take everything Sn equivariantly. So these are all Sn equivariant fundamental groups. Okay. So as a corollary of the theorem, what we see is we have a cover of this space, and cover is determined by an action of the fundamental group on a set. And because of this isomorphism, the cover of this space is entirely determined by its restriction to just Fn bar. So just this central fiber, the special fiber, determines the whole cover. I mean, the cover over the central fiber determines the whole cover. And so if we want to calculate the monodromy of this thing, which is sort of like our problem from the viewpoint of quantum cohomology, is to calculate the monodromy of this thing, because that's where the quantum cohomology algebras are varying. It's enough to understand the monodromy of the cover restricted here, and to understand this map, which goes like this. So we have a map that is here, and then we invert the isomorphism, so we get a map like so. So that's the statement of this corollary. Any question? Why we want to understand the monodromy action? Well, I don't know. That's somehow the game we decided to play. Like, again, like maybe just to remind you of the viewpoint is we had this quantum cohomology algebras, or quantum multiplication by divisors, and which depended on a parameter Q, which lived in this open subset of the torus. And then first step, we saw that we could compactify that family to this interesting compactification, namely this Deligne-Mumford space. And now we have a family of operators depending on points in this Deligne-Mumford space. And now we're interested in what happens to the eigenvectors for these operators as we move around this Lie-Mumford space. I mean, why should we do it? Not sure, but it's supposed to be, as I said at the beginning, or not at the beginning of last lecture, it's supposed to be analogous to this Bezer-Kovnikov-Okonkov idea of introducing the quantum connection and taking the monodromy of the quantum connection. Yeah.
From this point of view, do you expect some compactification, some categorification of everything that you have?
Yes, sort of, yeah.
And this should work with this loss of story?
Yeah, that was the idea. Okay, let's continue. So I still have to tell you what these groups are. And why is this cactus word? Well, the cactus word is because of the nice pictures. But okay, here's the groups. So here's 3 groups, cactus group and its variants. Okay, so I begin with this cactus group. So cactus group, what is it? It's a kind of analog of the braid group. So it's a finely generated group with a map to the symmetric group. And how is it defined? Well, it has many more generators than either the symmetric group or the braid group. It has n choose 2 generators. Those are the generators. All the generators square to 1. So just like generators in symmetric group, the generators square to 1. And maybe I should emphasize that this Cn maps to Sn, and this Sij maps to the permutation that looks like this. So that's a permutation which completely reverses the section between I and j. So like the longest element on that subset. Okay. So that's what Sij is. So what are the relations among the generators? Well, besides they square to 1. So if the generators correspond to disjoint intervals, so I think of the generator as being corresponding to an interval. If I have generators corresponding to disjoint intervals, they commute. And then if I have 2 generators where one interval is contained inside the other interval, the generators don't commute. The outer one conjugates the inner one, like by kind of flipping it inside of the outer interval. That's what that formula means. And so this is the cactus group. It's like a non-trivial, infinite, finely generated group with a map to the symmetric group. Close cousin of the braid group. Yeah? There's just no relation. So that kind of allows the group to become infinite. The generators just can start piling up. Yeah. Okay. So now a second group is the affine cactus group. So affine in the sense of like affine Dynkin diagram. So this first cactus group was like based on the an minus 1 Dynkin diagram, and this second cactus group is based on the an minus 1 tilde Dynkin diagram. So I have so I did the same thing as the original cactus group, but I have generators corresponding to intervals on a circle. So this is supposed to be a picture of an interval along a circle. So maybe n equals 6. And here I have just, besides like the most like obvious intervals, like 1 up to 4, here I have an interval which like starts at 5 and ends at 2. So an interval like that along the circle. And if you just do exactly the same relations, but with these like more additional kinds of intervals on a circle, you get the affine cactus group. And finally, something called the virtual cactus group. Virtual here is in the sense of virtual knots. That's where the name comes from. So what's the virtual cactus group? We have, we start with the cactus group and with the symmetric group, and we form their free product. So a priori, no relations between elements in the symmetric group and elements in the cactus group. But now I introduce a relation. The relation is the following, that if I have a W is going to be from the symmetric group, Sij is going to be a generator of the cactus group, and so the element of the symmetric group sometimes will like conjugate, and we could put the W inverse here, sometimes we'll conjugate this element of the cactus group to a different cactus group generator. When does it conjugate? Not always. I mean, if I always let it conjugate, I'd get the semi-direct product. But I don't let it always conjugate. I only let it conjugate sometimes when W is a translation on the interval ij. So when the permutation W looks something like this. Oops. Okay. I don't like that. When the permutation W looks like this on the interval ij. It does whatever else, but on the section between I and j, it looks like a translation or like a cabling, you could say. So in that case, we have this relation, and that's the definition of the virtual calculus group, and that's the group that entered. So now that you've seen the groups, first I'll tell you the following couple of things. There's inclusions from the calculus group to the affine calculus group, and from the affine calculus group to the virtual calculus group. So from the calculus group to the affine calculus group, it's kind of obvious because you have less. The affine calculus group just has more generators. From the affine calculus group to the virtual calculus group, it's a little bit less obvious. But what happens is that those like kind of extra generators that go around the circle, they can be written now in terms of like the rotation element in the symmetric group and ordinary generators. So that's the nature of this map.
That map is realized geometrically as a whole?
Yes. And so all these three groups are the fundamental groups of some spaces. And let me begin at the beginning, and then I'll return to the picture above. So at the beginning is this theorem of Davis, Januszewicz, and Scott from like, I guess 30 years ago, roughly speaking. And their theorem is that this calculus group is the SN equivariant fundamental group of the real points, standard real points of this Deligne-Mumford space. So that's where the calculus group originally came from. So there it is. In fact, maybe I'll draw a quick picture. So remember, what does a point in the Deligne-Mumford space look like? Well, it's like n points on a circle. And what you can do is you can imagine a path like so, where the points between I and j have gone off onto their own component and then come back in the opposite order. And like a path like that in the space corresponds to the generator of the calculus group. That's kind of the idea behind this isomorphism. And so then this isomorphism is kind of generalized to the theorem that I stated above. So here we had this variant of the real locus giving us the Fn calculus group, and this Fn bar thing giving us the virtual calculus group. And yes, the map here coming geometrically between spaces is realized in terms of this map that I described above, below. And actually this, well, okay. Let's continue. Any question? How am I doing on the time? Must be a... Wow, I've been talking fast today. Okay, any questions? We can slow down a little. Okay.
So how did you identify the right real structure? So this was something that came out when you were trying to compute things, so you already knew that was the right one to consider?
I mean, the truth is it's not, there's actually, you can also take, I mean, this one looks very natural because it's like kind of this, in this real structure here, all those just like the obvious real structure, all those delta ij's are real, everything defined over R. So the only question is why to take this funny real structure here. So I think there's like, first of all, you can actually take just the standard real structure, and we have a similar theorem, but you would have to change this group. There's a different group. What? Well, it's some other variant of the calculus group. So, but I actually think this one seems to be the more natural thing from the viewpoint of this kind of categorification that you mentioned, that you were asking about, because somehow from the viewpoint of those like Bazir-Kovnikov and Losev stuff, they have this categorification in characteristic P, and because of categorification in characteristic P, you have this wall and chamber structure, which is periodic because of the positive characteristic. So you have like this kind of affine wall and chambers structure, and that kind of seems to be related to the appearance of the affine calculus group here. So from some abstract point of view, that's why I would say. But otherwise, we just picked it. Well, you have to be able to pick it. I mean, if you pick some random real structure, you might not be able to prove this kind of theorem, right? So somehow you have to pick a real structure and at the same time prove that this algebra is generated by operators that act like by Hermitian operators on your vector space. And so if okay. Okay. So okay, I said this in words a couple of times. Okay. So now our goal is to understand the action of this virtual cactus group on these fibers. And so now we have to change topic again. Because when I say understand, we want to understand in some combinatorial way. So now I'm going to introduce the combinatorics that we're going to use to understand the action of this virtual cactus group. Okay. I have a little more time than I thought I would, so maybe I can even draw some more pictures. So, okay, so to every representation of a semi-simple Lie algebra, there is a combinatorial object associated to it called a crystal. So maybe some people have seen it before, maybe not. So a crystal is a graph. The vertices of the graph is a basis of the representation. And the edges of the graph give you the action of EI and FI on the basis. So maybe just give you quick examples. So for example, we could take like the representation, say, two-dimensional representation of SL2, three-dimensional representation of SL2. So then, well, I have three vertices because I have a basis, is three things. And the action of like, I have some lowering operators F and some raising operators E. Okay, that wasn't super exciting example, but let's say an example of a graph. Here's another more exciting example. Let's take a joint representation of SL3, or the representation of SL3 with highest weight 210. This is a joint representation. And then this representation is 8-dimensional, and the graph looks like so. I just draw the lowering operators. This red line is for F1, and maybe this green one is for F2. Notice something slightly non-trivial is going on in the middle there. Okay. So it's some combinatorial, like these arrows, those vertices only, each one has either a green coming in and green going out, or a red coming in and red going out, and not both. Okay, so there's some procedure to every representation of semi-simple algebra forming this combinatorial object called a crystal. It was originally defined by Kashiwara. Well, Kashiwara just won the, what prize? The Abel Prize, partially for this theory. Okay, maybe for other things too. And one thing that's really interesting about this crystals, which I don't really have time to get into, is that just like you can form tensor product of representations, you can form tensor product of crystals. So what does it mean to take tensor product of crystals? Well, it's supposed to be like a basis of the representation. So if I took tensor product of vector spaces, I should take Cartesian product of the bases, right? So the underlying set of this crystal tensor product is just the Cartesian product, but this set carries an unusual graph structure. Let me just draw it for SL2, since we have some time. So let's take V2 tensor V1. So the three-dimensional representation tensor the two-dimensional representation for SL2. So there's the two-dimensional representation, there's the three-dimensional representation, and there's their Cartesian product. So, those the left side and the top side are like the inputs, and the rectangle in the middle is the output. So I have to somehow figure out how to draw the arrows through the middle part. And how are you going to do it? Well, when you have a Lie algebra representation, right, like EI acts on V tensor W is equal to EI on V tensor W plus V tensor EI of W. So there's a plus. But we're in a graph, so we can't have plus, so we have to choose one or the other. So for every vertex, we're either going to decide we're going to go right or we're going to go down. And if you think about it a little bit, you probably will come up with the following thing that seems like the only sensible thing you can do. Like that. And notice this matches the decomposition of V2 tensor V1 into V2 tensor V4. Yeah, that sounds right. Okay. So the So in this crystal tensor product, there is a definition of this tensor product, but it's kind of not symmetric. Like it doesn't, it's not symmetric in the role. You get a kind of like a different structure on the same set if you switch the roles switch the orders. Now, way back, 20 years ago, together with Andre Henriques, we showed that this category of crystals forms something called a co-boundary monoidal category. So there are these well-known things called braided monoidal categories, like the category of representations of a quantum group. And if you have a braided monoidal category, then there's an action of the braid group by the structure of the category. And in co-boundary monoidal category, it's a sort of strange cousin of a braided monoidal category. And instead of having an action of the braid group on tensor products, there's an action of a crystal on tensor products. And this category of crystals is the only natural example I know of a co-boundary category, but it is really a non-trivial and interesting co-boundary category. And so we get action of this cactus group, so this CN here is a cactus group, on such tensor products of crystals. Just like in a braided monoidal category, you would get action of the braid group. Now, on the other hand, this tensor product of crystals as a set is just the tensor product, underlying Cartesian product of the sets. So because of that, Sn can just act in the obvious way on permuting the sets around, right? Like the usual way it acts on a Cartesian product. Sorry, I'm always like slightly lying here in that like I have like a single fixed lambda 1 up to lambda n, but when I act by either this or this, it's going to like permute the copies around. So I should really always, I just suppress it because it's like a little ugly, but I should like put the union over all lambdas everywhere here. Otherwise, it won't really act. Okay. So these two things act on such products. And so on this underlying set of this crystal, both groups will be acting because this will be act because of it's a co-boundary category, and this Sn will act because it permutes things around. And maybe surprisingly, those actions are completely have nothing to do with each other. They're not completely don't have nothing to do with each other, but they're really different actions. Like one doesn't factor to the other. And okay, so in our paper to come, hopefully in the next week or so with Leonid, we're going to prove that these two actions combine together to give an action of this virtual cactus group. So what does it mean? The virtual cactus group is by definition a quotient of the free product of the cactus group and the symmetric group. So if you have an action of the cactus group and the symmetric group, the free product will definitely act. And then there are like a little bit of relations that I explained in the definition of the virtual cactus group. And it's not hard to see those relations will be satisfied for this action. And so we'll get an action of the virtual cactus group on the underlying set of this crystal. Okay, and this is great news because we wanted to describe, combinatorially action of the virtual cactus group as this eigenlines for this inhomogeneous Gaudin algebra acting on this tensor products. And now we have a natural candidate because this set is the same size as that set of eigenlines, right? Because this set is the same size as the basis for this tensor product. And so in our paper that's about to come, we also prove this result, that we have a VCN, virtual cactus group equivariant bijection, between this product of the crystals and this set of eigenlines acting on this tensor product. And well, I didn't write it here, but this theorem is actually very easy because we did all the hard work in our paper about 6 years ago, which was also joint with Eva Halacheva and Alex Weeks. So it's kind of building on what we had already done somehow. Any question about that?
So it's from this theorem that you see an evident categorification because you relate Pisa basis with useful basis, so you mentioned that there should be some category of vector sheets that should appear, right? Somehow it's a natural from this, no?
Yeah. Yeah, you can imagine. Yeah, you can imagine that this crystals come from. So one way to produce crystals is via categorifications, and in fact, there's So a little bit of what you're saying to make it more precise. There is a paper by Losev, Licata, Halacheva, and Jacobi. And in that paper, they proved that when you have a categorical, when you have like category of modules for KLR algebras, so like this kind of categorical representations of your Lie algebra, then you can use it to give actions of cactus groups via these perverse equivalences. So that's pretty close to sort of categorifying this. Somewhat slightly different, but it's close to this categorification of this, yeah. Yeah. A perfect basis or a basis? Well, the bases you get this way of these eigenlines are not, they're kind of not directly related to these like perfect bases or canonical bases. So none of the bases that are of these eigenlines will be canonical basis, good basis, perfect basis. None of those things can possibly appear this way, strangely enough. But they still, like, I mean, somehow we still prove this theorem, and somehow having, like, so one thing about this, like, you know, these special kinds of bases is that they're, like, nicely compatible with each SL2. And this base is not very compatible with each SL2, but you have the freedom to like move this theta around. So you kind of gain something because you can move theta to a special place, and then you are compatible with SL2, with your given SL2. So this it's somehow like a different. I have a lot of work about studying those kinds of bases, but this is like an orthogonal direction, surprisingly. But yet, combinatorics is retained. Yeah? Well, so if you took the fundamental group of the regular locus and the Kähler torus complex points, you would get like an affine braid group. And this way you get like an affine cactus group. And so it's kind of weird cousin of that. And there is a weird relation between, at least forget the affine for a second, there's a weird relation between the cactus group and the braid group, which is there's a map from the cactus group to a certain completion of the braid group. So there is a little bit of relation that way. Okay, I'm basically done, I think. So the conclusion of all this is the following. So our goal, which is what we wanted to do, which is study the monodromy action of this fundamental group on the eigenvectors for quantum cohomology of affine Grassmannian slices, is given as follows. You take your the fundamental group is the affine cactus group. You take the affine cactus group, you map it to this virtual cactus group, and then this virtual cactus group acts on this product of crystals as I described. And I mean, this last step you can really compute, like this cactus group, like you have a model for crystals, for example, by Tableau, and you can go ahead and understand exactly how you can compute how this action works. So this is completely combinatorial now. And that's all, yeah.